Hello and welcome. Thank you for joining me today for this presentation on the rendering architecture of Roblox. My name is Angelo Pesce. I head the rendering team at Roblox. I'm a senior TD there. And before joining Roblox, actually, I've been working in the video game industry. I shipped a dozen different titles for, I think, 5 different companies, ranging from smaller studios like Milestone in Italy, Relic, Capcom here in Vancouver, and then also for very large publishers. So I had some experience at Electronic Arts on the Finite series, part of EA Sports. And before Roblox, I spent a little bit more than 4 years as a TD in Activision Central Technology, mostly helping studios involved with the Call of Duty franchise. Before we jump into what is Roblox and the meat of this presentation, I wanted to spend one slide on why I'm here and why I was very eager to help organize a conference around game engine architecture. Having seen a few different games through a few different companies, what is interesting to me is that in the end I managed to accumulate way more questions than answers on the design of rendering engines and workflows around rendering engines. So, from kind of low-level decisions, I've seen engines using Siggraphs, I've seen engines using flat lists, rendering through stateless objects or stateful kind of command buffer abstractions. Should we do a specialized data structure per object type, or is it better to have a generic kind of class that encapsulates a vertex buffer like a mesh shader and the resources needed to perform a given draw? Should we go through virtual functions and interfaces, or specialized loops per concrete type that take lists of objects and generate the underlying drawcalls for the GPU API? I've seen even some engines that were recording snippets of the actual command buffer, but argumenting them with a sort or call information in order to be able to do that multi-threaded and then merge sort and issue the actual final draws. And when you go to high-level kind of organization, it's the same for me. Seeing companies like Electronic Arts that really leverage its size on the idea of trying to find the next great piece of shared technology, worked for similarly large publisher like Activision, which on the contrary leaves to the studio all the decision on their technology, and that mostly means that every studio has its own branch or engine or code base really. And everything in the middle, right? There are companies that have maybe one engine per franchise or per genre, but even some other smaller companies still had like all different engines per each product they made. And I don't know, never had a definitive answer of what is the winning idea among all those. I've seen successful products taking decisions all over the spectrum, right? Even to the degree of how much rendering is driven by artists and technical artists versus having everything hard-coded, perhaps more performant in doing what it does, but harder to explore different visual effects, right? And even to the graphic techniques, right? At Activision, I've seen Call of Duty shipping with pure forward, renderer, tens of thousands of shaders per levels, lots of drawcalls, trying to statically specialize forward shaders. 2 systems that were purely deferred renderers and really lowering back on the amount of specialization there, to something in the middle, leveraging forward plus, some ideas about this buffer, and in the end, I've never seen one idea clearly winning over another. So, in the end, I kind of grew this impression that the reason why I don't have a great answer is that at best, technology is there to serve your people, your studio culture, and the specific of your product. And so you don't have an abstract notion of technological or even workflow optimum or beauty. And beauty per se, it's not even the correct metric, right? Great engineering is not about having an abstract best possible code base or engine, but even to the degree that we have tech debt is not entirely negative, right? That is a thing that we can leverage, and if leveraged correctly, it can actually help your product, right? And also, I strongly believe that all non-trivial technology is a matter of trade-offs, and there is no single way to success. Your studio history, your product history, your studio culture shapes the engineering, the actual code base. If you wish, this could be seen as an extension of Conway's law. And this means that really any theory that we want to formulate, anything that we talk about when we talk about engine architecture, should be considered in context. And so, what is the context here? What is the context of Roblox? Most people coming from video games and AAA game development are quite unfamiliar. So, I tried my best to not take a lot of time here and condense the ideas of the Roblox Metaverse in 3 slides. So, let's go. First thing, I would say Roblox is not a game engine. It's not a piece of middleware. You don't pay some licensing fee to get some source code or some tool to create your product. In fact, there is no way to get Roblox, and it wouldn't really make sense. What would you get? The code base per se is not that useful. There is like this gigantic infrastructure around it that you wouldn't be able to duplicate. And even if you consider all the technology, right? So the engine code base plus all the services, all the infrastructure, that is not entirely what Roblox is. When you decide to make a game in Roblox or an experience in Roblox, you do it also because you want to leverage its community, the players that are using that platform and socializing through it, right? And that is another thing that you would not be able to replicate. At the same time, I don't think that Roblox is entirely a virtual world. We don't have a single default shared world, not even a default lobby or a space that you get, you jump in when the first time that you open Roblox. And so in that sense, it's a little bit more like a game engine, meaning that you can create anything you want. It's not a single virtual world. And we try our best not to dictate the art style or impose constraints. We do not want to populate Roblox with our own art and content. But there are certain out-of-the-box defaults, let's say, that make sense. So when you start developing Roblox, you are kind of guided, or default toolset is made to create somewhat realistic social spaces. So you start with a third-person avatar, you are in physically simulated worlds, and all this physics simulation is modeled after real-world kind of concepts. So if I had to say what Roblox is, well, I would say that Roblox is a social network for creativity. Think more YouTube and Instagram rather than Unity or Unreal, or even Minecraft and Fortnite. So I have my identity in Roblox, I create my avatar, I create my persona, and I connect with others through Roblox, either by playing in social spaces with others, or through creativity. And even creativity in Roblox is social. The Roblox editor has this modality, which is the default one, called Team Create, where you join in with a bunch of friends and start creating together a new 3D world. So in that sense, I would say it's more similar to an Instagram. Instagram creativity is photos, you express yourself, you browse what other people made. Not the only difference, but the main difference is that in our case, we don't deal with photos or videos, but with interactive 3D worlds. Last slide on introduction to Roblox, or the context that we operate in, is Roblox the company. So it started actually in 2004 with a product called Dynablocks. It was an educational playground, physically based. And it has been there, then again, for more than 15 years. But it was a small company for a long time, and it's still relatively small. So, for example, in rendering, for most of Roblox's lifetime, there was basically one rendering engineer. And even in 2018, a couple of years ago, we had around 4. Today, we have 14-ish, depending on how you count, which is a good-sized team, but it's definitely not gigantic when you compare it to other game engines out there. In total, I think today there are around 700 engineers in 77 teams. And of course, the scope of Roblox is pretty sizable because it combines all the problem set of a 3D game engine with all the problem sets of a social networking website, right? So what are those virtual worlds? How are they expressed? How do they work in Roblox? Well, we have this thing called the data model, and the closest analogy is to think about is the HTML document object model. Instead of JavaScript, we have Luau scripting. And in the data model, you'll see there are multiple root services. So it's really a forest, but the tree nature of it is mostly so you can keep your object organized. There are no default inheritance semantics. It's not a transform tree or Carlin tree. The relationship, the parent-child relationship, do not propagate rendering attributes or other things by default. Some objects do affect children, but they're special objects. There is no default kind of tree semantics in the workspace. And so the workspace is where all the objects representing the 3D physically simulated world will be. And then there are lots of other services. I will show there, I highlight there only one, the lighting one. Under the lighting service, you will add objects that are not part of the physical world, but they affect the rendering, the visuals. And this data model is natively client-server. So we have these RBXL files, which are similar to an HTML. It's the static content, the state of the world as it starts. But the game clients do not get served the RBXLs. Servers load them, and then the servers, when a client joins, start replicating parts of the world to the client. So all the objects and properties get streamed from servers to clients. And you can choose, depending on the size of the world, if you want the entire world to be loaded at the beginning or to have streaming enabled. But in general, you shouldn't expect clients to have your entire game world. It will be streamed in and out. And you shouldn't expect to have exactly the same game world through the different clients because we can stream things at different levels of fidelity. And as I was mentioning, our scripting language is Luau, and the way that this works client-servers is that by default, the scripts you create are server-side, and all the logic is server-side. And any change that those server-side scripts make, by default, replicate. But you can create also local scripts that will be executed only on clients, and those should be scripts that are only for presentation code, things like camera manipulation, UI, stuff like that. It shouldn't affect the 3D world. And so client scripts are sandboxed, and the objects that you create to client scripts do not replicate back to the servers and to the other clients. All right, and what are the worlds made of? So under the workspace, what primitives you expect to have? There are a bunch, but I'll show just a couple. The main primitives of the worlds are things called parts, which are simple geometric primitives. Those have cubical projected textures, and you can assign decals and other ways to customize their colors. They can CSG. The CSG system is also working runtime, and they do exact collisions. The other main kind of object type for 3D graphics are mesh parts, and those can be UV mapped, or you can just use the cubical projection as well. They get convex decomposition for physics, and we have an automatic LOD system, so the meshes can change their fidelity based on distance. And even adding mesh parts, which, I mean, meshes in a 3D engine, it's kind of obvious, right? But it was really not easy. The first attempt was actually all the way back in 2006. And they needed to get pulled for a variety of reasons, including moderation, in 2008. And they got added back in their final form, the way that we have today, only in 2016. So 10 years after the first time that they were attempted. And this year, we are augmenting them with support for skinning. There are a bunch of other rendering primitives. We have a terrain system that is made in voxel. We have particles. And the other thing that it's important to notice is that we have this concept of materials. And materials for us are not just textures and shaders, but they carry also all the default behaviors. Right? They are physical materials, so they have physics with them, they influence audio, they specify all the characteristics of a given part or mesh part. And all right, of course, I mentioned that Roblox is natively client-server, but that's not all there is to it. So the servers, we call them RCC, the Roblox Cloud Compute. They are a Linux build of the game engine. But of course, there are also a lot of other cloud services. And Some of those are developer-facing, so analytics, data store, marketplace. There are a lot, of course, of services that are internal for Roblox, but one that is very notable that I have to talk about it today is what we call the asset service. So what are assets in Roblox? Assets are pieces of binary data that are immutable. We do support versioning from users so they can update them. And they are delivered through CDNs and content addressable storage. This is optimized for high bandwidth, but it is a high latency system. And examples of assets at Roblox are things like images, mesh, sounds, animations, all things that are not part of the mutable state of the world. And the fact that they're immutable is very important because it means that we can moderate them. We have a fleet of human moderators. Of course, we augment that with AI. So when you upload an image, moderators can look at it and approve it if it passes moderation. And this is the lifetime of a typical asset. So you upload it by hitting a web endpoint. The web endpoint validates your data, normalizes, strips away all the things that we don't care about or shouldn't care about. Then the uploaded asset goes into our moderation queue. If the moderation passes, so your asset is approved, writes into the database, now your asset is accessible, and we kick some initial processing. So certain other types of assets, for example, need to generate thumbnails so you can browse them and see them in our web interface, or some kind of format conversion, stuff like that. Now, after moderation, your asset is accessible. The client can come, request it using its asset ID, and this asset ID gets resolved to a piece of binary, which is the best available version that we have for a given platform. So the asset ID is unique, but the actual binary data that you get on client can change based on the client that you're on. And how does this work? Well, at the beginning, chances are that you will get just the unoptimized asset. Let's say that we were talking about images and textures. So before the kind of raw form for us are PNGs. And if no processing was done on the asset, you will get delivered to the client just an PNG, and there is no GPU compression. But as the asset gets accessed, it goes into a queue where we perform what we call optimization. So in case of textures, we start kicking texture compression, DXT, etc. for a variety of clients, a variety of resolutions, so on and so forth. And the reason that those optimizations are done lazily is because, well, a lot of assets do not get accessed, but also we need to be able to update the internal formats and the tools that generates those optimized formats. And so if we had a system that could only do things eagerly and in batches, well, we have petabytes of data. When a tool, say we find a better way of doing ETC compression, we cannot realistically go and transcode all the PNGs in this new format, right? So we have internal versioning. We see that optimized version is obsolete now, and we re-kick the optimization, which will generate a new version of the compressed asset. There are ways that we can batch process, but it literally takes months to go through the entire database and do those kind of reprocessing. And all the rest, like everything that are not assets, is basically dynamic. Like 99% of the properties of objects in the data models are mutable, and they're exposed to Luau. And to the degree that even Roblox Studio or editor does not really have modeling facilities of its own, is basically an interface on top of the data model that it's used in runtime. So everything that the studio can do, or 99% of the things that the studio can do, the games can do as well. And this allows a lot of games to be creative in nature themselves. So if you want to make a game that has, I don't know, maybe something like SimCity, then yeah, why not? We do not make our editing tools to be available only in the studio side of things. And as I already mentioned a couple of times, everything has physics by default. Physics are server side, but we have a method of ownership where your player and things near your player can migrate to the clients as well. So some examples, right? We don't have a notion of static objects. You just take parts and you bolt them to the world. You use anchor constraints. Models for us are just collection of parts and mesh parts, and maybe you just weld them together so they move together. Even our avatars are just a bunch of parts put together in kind of a special container. And the idea of rendering is that we really have to infer optimizations from the data model. So the objects in the data model make sense on their own. They are primitives that make sense for virtual worlds. They don't try to be particularly engine friendly. We don't have things like instancing. We don't have even, you can't really reference the same model multiple times. You just take and copy and paste it a million times in the world, and the engine has to cope with that. As I mentioned, we don't have a transform hierarchy. So if you want to transform something that has 10 parts, you will change 10 C-frames, 10 matrices. And to give an idea of scale, we have one test place called Roblox Battle Royale that has 50,000 parts, and they're fully destructible. Another kind of internal test place is our town hall, where we do our weekly town halls. And that right now can host around 500 players, 500 avatars, all in our square. The town hall is a replica of our office space in San Mateo. And so, yeah, the idea of the data model is that everything is tech agnostic. And you have to think that this platform has been there already for 15 years. So if we create anything that was meant for a given technology and a given era, it would quickly be obsolete. Instead, the world is built with this high-level kind of universal concepts. We don't have things like, occluders, portal, lightmouse, all those concepts that are really linked to a specific technology. We don't allow them as primitives in our virtual worlds. And nor we allow people to, tweak tech-specific parameters like a shadow map bias or the number of samples in SSAO, or even the fact that there is an SSAO. One thing that is acceptable is, though, hints. So people could say mark a given model to be less important, and we know that we can maybe LOD or optimize streaming in different ways. Altering intention is fair game. It's something that people can be part of our data model or object properties. This seems to be a quite big set of constraints that are fundamental for the viability of our platform, but it's interesting because they turn out to be also features. Because this idea of basically tech agnostic authoring makes the creation of virtual worlds much easier. It turns out that a big part of why real-time rendering and video games are hard to author is because you have to think in terms of your underlying technological implementation. And also it makes our virtual worlds in a way, or our creation, more social. Because things have their own strong semantics, it also means that chances are that, say if I make a car, and I even, as part of my car model, have a bunch of scripts that control and maybe some effects and particles and stuff like that, I can package that and share it, and someone else can take it for its game, drop it, and chances are that it will work, including all the behaviors that it carries. All right, so how this context shapes our engine design? Well, it turns out all those constraints make us make for a really hard problem, right? So we don't, as a recap, we don't allow content to be hand-optimized. We don't allow content to know about the technology. We deliver to hundreds of thousands of different devices. Most of them are low power or kind of obsolete because a lot of our audience is made of kids. And we said everything is dynamic. We don't allow pre-computation. We don't want the editor to be in any kind of have special technology that it's not exposed to the runtime. And we have this idea of distributed computation. So we have clients, which are, of course, low latency, but also relatively low power. We have servers, so we can decide certain computation to be done server side and just replicate to the clients. This is how our CSG today works. And then we have this high latency, but we can take all the time that we want, which is the cloud, where, for example, we can now do things like optimize the texture compression or LOD on meshes, or maybe in the future other kinds of ideas around meshes, maybe generating occluders or whatever you want to imagine that would take some time, but you can share across different games. And yeah, we have a relatively small engineering team still. And to give another example of how hard this is really like kind of day-to-day, simple thing, profiling, right? This is something that all engine developers face. At our scale, it's really data analytics, and it's a big open problem. for us. Testing on device, using vendor tools, all those kind of things we are very familiar with, has limited usefulness. We do it mostly to test that things work correctly and they are in the right direction. But we have so many different devices, and so many games, and so many settings or contexts for each game. It's really complicated to understand most non-trivial changes, what effect they yield on the platform. And of course, a given change does not interact just with so many different devices and so many different games. But there are also some other kind of side effects, if you wish. The engine itself has load balancing. If you maybe optimize memory, then the streaming system can stream more objects and things can be now slower because a given client can fit more of the world. We have things like thermal throttling that can be affected, right? So it's really not clear in a lot of times when we do certain code changes, what part of the device and game population has been affected and in which direction. So how do we solve all this? Because at a given point, right, we have to find some ideas or some shortcuts. So the first thing that we do is to resign the idea of being optimal. It's too hard even to understand where we are. And instead, we think on everything that we do, we try to make it scalable. So clients, the idea behind the game client is that they should always work. Of course, never crash, never go out of memory. But in general, always work. And if we need to, we can scale quality arbitrarily. We never promise any kind of fidelity. And we always improve it as well. So you really cannot auto towards a given fidelity. That also means that if we need to, we can go all the way to flat shading. We do not, but almost, right? We could, though, right? We can start disabling effects, fallback, like everything that makes your game, that keeps your game still playable, it's fair game. And the other idea is that we prefer most computation to be time sliced, so done incrementally over time. This means that a more powerful device will see no lag in its rendering updates, but a low power device, well, it will have maybe a lot of lag, but it will still work. So we have this concept called a frame rate manager. This is the overall monitor of rendering performance. You can think of it as similar to dynamic rendering resolution in a typical AAA game, but instead of just controlling the rendering resolution, in fact, it doesn't, they control the rendering resolution. What it does, it controls all the other rendering parameters, things like draw distances, LOD distances, but also what rendering technology we use. And originally this was really designed to control CPU performance, and now we are modifying it to be aware of both CPU and GPU bottlenecks. For example, the actual rendering backend, we can go from having only the sun being analytical and not even shadow maps, cache everything in voxels, all the way to our latest, like most high-end backend, which has only analytic dynamic lights. It's all cached, tiled, EVSMs, both for the sun with cascades and for all the local lights, and it renders everything with Forward Plus. So this is kind of one of the key pieces that allows for us to scale. And then again, it's really non-trivial, because to understand how the heuristics, how to tune things on such a large population is then again a data analytic kind of machine learning, if you wish, problem. Right now, the frame rate manager just tries different settings throughout the game execution, and then it caches on device the setting it thinks is best for that given experience. And this is the other axis on which we cheat, like being patient, if you wish. So we know that we will never win over any AAA game at a given moment in time, but our clients never stop evolving. You can see there's some example of the evolution of our terrain system and its rendering quality. So the idea is that, well, eventually we will catch up. Our virtual worlds are not static. They are not products that get shipped, put on a DVD, and then it's that's the end of it. Because the authoring was never done in a way that fixes the technological choices, we are constantly improving and constantly evolving. So quick recap, performance has to be about scalability, good to cache rendering data and compute everything over time. And we will see we work through a few different levels of abstraction in the actual implementation. Which brings me to the actual implementation of the Roblox rendering engine as of today. So the rendering engine, kind of core of it is, if you wish, fairly old school. So we run with the classic 2-thread model. We have a simulation and a rendering thread, if you wish. We call them main and render. And the communication between the two is done in a step that we call render prepare. Render prepare, what it does, it locks the data model, so no change can happen, and it fetches any relevant change that happened from the previous rendering frame. And then, well, it tries to do that as fast as possible because, well, now you're locking, right? So you don't want to stall the simulation for a long time. And after it fetches all those changes, it unlocks the data model, simulation resumes, and in parallel, we start what we call the render perform, which is where we generate our actual draw commands. And the entire threading system itself is fairly old school. So, of course, we have a thread pool, we have tasks and jobs, and we don't create and optimize graphs. But we have this idea where jobs can create other jobs, which really makes it easier to do graph-like computation. Originally, this was actually created more to do computation asynchronously in quanta across different frames, rather than being very widely multi-threaded. And this is because, as you can imagine, a few years ago, we didn't even have so many threads, right? So the original idea was to do things very incrementally over time. Now, there is some discussion on whether or not this architecture is maybe suboptimal. There are some theoretical advantages of a job graph. But in the end, I think that this actually old school arrangement is simpler to reason about, is simpler to work with, and it will serve us for still a very long time. We're very far from pushing the current system to its limits. I'm even kind of doubtful that at its limits it would be necessarily less optimal or more complicated for the same performance than a full-blown graph system. We'll see. Let's have a look at the sequence of rendering step by step. We are mostly an event kind of push system. So we have parts and mesh parts, as I was mentioning in the data model. They derive from a common instance type, and this instance type provides support for reflection and events, and then hooking to listening to events. Then we have this interface called GfxBinding, and this is the common interface that attaches to instances and listens to property changes that are relevant to rendering, and to add remove child, so when new parts and mesh parts appear or disappear from the scene. From then on, every rendering subsystem implements the GfxBinding interface for the data model objects it directly manages. And typically, what this implementation does is just to mark or queue certain rendering structures to be invalidated during the prepare phase. We have like a different systems for the GUI, which is based on recording a kind of virtual command buffer, but I will not really go into that. So after parts move, they trigger certain events, they go through the GFX bindings that invalidates or queues things to be invalidated. We reach the prepare phase. Prepare locks the data model and goes through those queues of invalidated objects and fetches all the information, like for example, a new transform matrix or a new value of a part transparency or material or color. So it fetches this data from the data model and trying to be as lightweight as possible, and it queues the data for the subsequent rendering perform. In the perform step, so now we unlock the data model, next frame simulation is starting, rendering is doing its job of generating Drawcalls, and the perform is organized in a bunch of different systems that we call clusters. The main idea why we have these clusters is that we never draw the data model objects one-to-one, so we never do one Drawcall per part. We always want to achieve something like 100-to-1 objects to draws, and so that's why all the rendering systems are called clusters. And we have different clusters per data model object type, and sometimes we have different variants based on your API or your underlying hardware capability. So the assumption here is that you have a lot of dynamic objects in a scene, but only a tiny fraction actually change, and so we can leverage that to construct bigger Drawcalls and then just invalidate certain of those and repopulate when objects change inside of that Drawcall. So today we'll just go through two our main clustering systems that handle both the parts and mesh parts. And those are clustered spatially in a kind of a hash grid arrangement. We have two clusters for those. One is called FastCluster, and the other is Instance Cluster. They both take care of the same data model objects because, in this case, the two clustering systems are meant to work on different devices. But we have many other clustering. So the terrain rendering is what we call smooth cluster, and then we have another clustering system that generates our what we call decorators, that right now is the grass that goes on top of the terrain. We have far imposters for faraway models, and those get rendered with a system that we call model clusters. And the idea there is that the imposters don't have textures, they just have vertex colors, so we can instance them, and because you may have the same tree instanced a million times, we detect this identical instances and perform the duplication in the model cluster. We have what we call GUI cluster for things like picture-in-picture, like little 3D scenes that are part of GUI. Long story short, there are many other subsystems that we won't see today. All right, so let's start with our FastClusters. This is a system that was made around 2012. And this was done around the same time as when we switched out of Augur to our own rendering system. And interesting enough, Augur was not even our first render, so we are on the third rendering engine change in Roblox. At the beginning, Roblox was based off Morgan Maguire's G3D, and then we briefly switched to Augur, and then we decided to create our own system. And our current code base, which is made of three packages, GfxCore, GfxRender, and GfxBase, it's around 10 times smaller than what Augur was, and hopefully a fair bit faster as well. All right, so in 2012, we went and switched to FastClusters, and this is the system that it's supported on any device. The idea of FastCluster is that on the fly, it will create index and vertex buffer to aggregate geometry that is close to each other. And we have few heuristics on how to split and create new clusters. Everything is underneath is grid-based, but we have a few different grids. We have one for large parts, we have one for small parts. And because reclustering is very expensive, right? Generating a new vertex buffer from scratch can take quite some time. We do that incrementally over time. So there is a budget for the vertex buffer generation, and if the budget is over, but we didn't manage to construct all the cluster that changed, we will do that next frame. As a further optimization, every cell, every spatial cell has a static and a moving cluster. So the moving cluster, if we detect that things are being animated, we create a dynamic cluster which passes up to 72 transforms as constants, and so it can draw 72 different parts or mesh parts in the same draw. And lastly, to further minimize the number of Drawcalls we need, some of the material properties get actually encoded as vertex data. in order to not need to break draws and issue different constant updates. Humanoids are a special case that is handled through the FastClusters as well. And the assumptions behind the humanoids is that, which is what we call our avatars, is that they will be basically all unique and they will be all dynamic. So they always use that dynamic fast cluster idea. But also because they're made of different parts that you can mix and match, to draw them in the fewest possible drawcalls, we have a system that atlas their textures. And this atlasing used to be done with render to texture, and now we are creating a system that actually creates DXT compressed atlas by rasterizing, having a little software raster that marks what chunks of the texture are used and creates charts by moving directly on full DXT blocks from the source to the destination texture. It supports 3 levels of MIP, so the MIP 0 blocks are 16 by 16. And we even have, we are creating a layered clothing system. And as part of that, we have an occlusion culling system. So if you have a shirt or something that hides the model, parts of the model behind, those parts, we will pick up they're occluded and not consider them in the texture atlas. All right, a few examples of fast cluster in action. You can see the different clusters being formed. And same, but more complicated. This is just plain fun. Said there is a second system called Instance Cluster, and this is much more recent. It went live around 2018. Same, it handles all parts and mesh parts, but it's for devices with working hardware instancing. In theory, in some situation, it may not batch as aggressively than the fast cluster, but in practice, it's not a problem, and those devices typically can cope with more draws, and it uses a lot less memory. It packs each instance in 112 bytes, and it is a hybrid static and dynamic instancing system. So clusters that are big enough, that have 70 or more parts, create their own buffers with all the relevant instancing data. All the remainder, like the few parts here and there, are aggregated dynamically per frame into their own instance draws. This is, of course, especially useful for transparencies that have to sort and would be different frame by frame and never be able to cluster otherwise. So in the end, overall, this is a huge win. Uses a lot less memory, and so we can render much bigger words through the instance cluster system. And this is purely using just the instancing capabilities. So today is not yet bandless. If you need to change texture shaders, it will split the draws. And this is also the system that supports mesh LODs, because it can render bigger words. It allows more things to be streamed in. We have our mesh LOD system that is implemented only if you are rendering through instance clusters. Finally, all the clusters generate structures that end up issuing the actual drawcalls. And even here, we still have a few levels of abstraction. So the clusters can directly access our graphic API abstraction, but we have a second abstraction layer in between that we call GfxRender. And that implements calling, like frustrum calling. It's another special hash. Sorting, so it has a bunch of different queues that then get sorted. And most cluster implements some common interfaces that go through our calling, shared calling and sorting system. Underneath, we have our own hardware abstraction, and that is mandatory for us. So no part of the code other than the GfxCore is allowed to directly call the underlying graphics APIs. All your interaction with graphic API has to go through GfxCore, and if there is something that is missing from GfxCore, you're expected to implement it. If it's available only on some platforms. You will create the equivalent of cap bits that then you can check and react to them as needed. So GfxCore today supports, well, a lot of APIs. We have not disabled, as of today, DirectX 9 yet. Even if it is deprecated, we will disable it in a few weeks. We support DirectX 11, 11 feature level 10, Durango version of 11, shader model 5, OpenGL from 2 to 3. I don't know if we're deprecating one of those, but all the GLESs, Metal, Vulkan, we actually have a huge penetration of the Vulkan backend. And it also implements all, the driver and GPU bug workarounds that we have encountered so far. And we have, of course, our own transpiler for shaders. So shaders are all written using HLSL. We control the number of shaders that we generate. We don't allow things to wildly permutated. And then our shader compiler has backends that output optimize HLSLs, PRV, Metal, and GLSL based on the platform. Okay, we are almost at the end. This is basically a whirlwind tour on how we do rendering and draws. But I wanted to show just literally two slides on how we perform lighting and shading, like the actual graphical technique. And even there, the idea is kind of the same. We try to decouple everything. So we have these clustering systems, then we have our calling sorting abstraction, then we have our hardware API. Those are the three components of issue and draws. And in general, the lighting and shading ideas are also decoupled from how the draws are generated. So which clusters they're using. Even if certain features, like say that certain rendering technology just makes sense for more high-end devices. So in practice, we will not implement them for FastCluster, for the older system. We will implement them only if you are on a device that supports instance cluster. And okay, I say devices, but it's not really, so the implementation can be only in certain clusters and linked to certain API capabilities. But really for us rendering, we don't control the rendering fidelity based on the device. Because even if you have a very powerful device, somehow we have to use the simplest lighting technology that we have available, because maybe you're rendering a very complicated world. And we don't control gain complexity. We don't know what the performance will be on a given device. And even we can't really associate the API level, say that you have a device that supports Vulkan, so you think, well, this is going to be very powerful. That's not necessarily the case. There are lots of recent devices that support modern APIs, but are very low power. And that's then again why we have the frame rate managers to orchestrate the quality level. All right, so what are those choices of lighting technology you may get? The most basic rendering uses voxel lighting. And we have then again, incremental, updated in time voxel caching system, which is all implemented in CPU actually, through CMID code for different architectures. And those are like chunks of voxels with skirts that get invalidated over time. And those chunks cache all the local lights, the sun shadows, and the sky occlusion. So the sun light is still analytic. The shadows are in voxels, and all the other lights are directly baked in voxels. We did an experiment with the GPU voxel computation a few years ago, which looked very nice, but hasn't shipped so far. The next step up from voxel lighting is shadow maps, and those basically replace voxel shadows for the sunlight. All the other lights are still cached in voxels, but if you get this kind of step up, if your device allows, then instead of having the voxel shadows, you get cached tiled, computed over time, EVSM, cascaded shadow maps. And kind of the final level that we have available today is Forward Plus, which leverage the same tiled EVSM infrastructure that we made for the Sun CSM, but now all the lights are analytic, all the lights are shadowed. And the only thing that remains in voxels as of now, if you are on Forward Plus, is the sky occlusion, which is the way that we basically differentiate indoors from outdoors. So all analytic lights use PBR, but you can go from a single analytic light to all analytic lights. And the shading math also can vary. So we have a custom approximation of GGX with energy conservation on more high-end fidelity levels, and we can switch to a simpler spherical Gaussian-based approximation for the lower end of the fidelity levels. And this is pretty much it. So the conclusions, Roblox so far. One of the key ideas, I think, in Roblox is this taking the long view in authoring. So we have to make sure we do not paint ourselves into technological corners. And we do that by being very careful when we change the objects, the properties, the API that it's exposed for creators through the data model. We design all our systems with the idea that one day the delivery, the engine, the client technology can change. So that's why I was showing that even our asset pipeline is made in such a way that we thought about, well, what if our data formats change and we have to invalidate petabytes of data? How we do that? And we do that. We change the engine, the server, and the cloud code literally all the time. And in the actual implementation, well, the tricks there heavily rely on incremental computation, heavily rely on caching, on this idea that everything can change, but only a little percentage of the world will. And even through the API design, we are helped in that. Like we don't have ways for Lua to bulk change millions of objects. So in a way, the speed of the Lua interpreter is also kind of putting a constraint on the number of objects that can change per frame. And in general, think about sensible fallbacks. Like if there is a new high-end, high fidelity effect that I can just disable and it doesn't impact gameplay, then great. That means that we can implement it without having to think about it too hard, because we can just add it to the frame rate manager. If the game is going too slow, we just disable it. And this is the end of the presentation.